All right, so let's see some reminders over here. All right, you know where to find the notes. For that one, I'm not gonna bug you anymore, right? You know where to download them. So the important exercise for you to complete will be the split array harder, right? Let me just remind you guys again, in case you haven't already started, you definitely have to, okay? You will see that in the lecture slide over here, you will see that we got the split array harder. You got everything over there, the starter, and I will definitely suggest maybe for the very first time, while it's still very new to you, you want to download the starter and give yourself a timer and then try to do it on your own, maybe within, let's say, 30 or 40 minutes, see how much you can complete. You can feel free to bring the incompleted work to me during the office hour. I can give you some advice. I think that'd be more valuable feedback for you. And after you have studied the example, I would say it doesn't matter how confident you might be, you may want to redo it, maybe with a less like a time constraint, right? You can definitely play with the example for quite a bit, okay? So that's one thing. And then last Thursday, even though our in-person class was canceled, again, sorry for that. The snowstorm is kind of way too early for this winter. Hopefully, I'm pretty sure it's not the only snowstorm we're gonna have, but hopefully the only one closure we have to experience, but we'll see. Make sure you guys don't fall behind, okay? So please make sure you catch up with the lectures over here. I would say last time is mainly about to really give you the broader context about why we're doing something more formally in this course about running time. But I think it's still very important for you to catch up, right? I'll give you maybe some very quick highlights today in the beginning. I think that'll be at least for you to follow the lecture today. I think that should be sufficient. But please make sure you follow through the lecture. It's definitely very important for your learning, okay? All right, and then guys, also very important, assignment number 1, right, has been released. All right, you got about 2 weeks to do it. I don't really assign any TA to the assignment just yet, but why don't we try my office hour? Since I got 3 hours per week, I definitely think that'll be sufficient for now. But if we really got lots of demand, in that case, I'm more than happy to maybe either myself holding more office hour or maybe the TA, right? So let's go with the 3 hours per week now. Okay, but you definitely have to get started assignment number 1. If I recall correctly, so there are several problems over there. Some of them are very similar to the basic one that we did in the review lecture for the recursion. So that one you can definitely complete first. But there will be some tricky ones which will take more time. And the best way to really get prepared for that will be to really do the split array harder. That'll be a very good preparation for that. Okay, and let's remind ourselves about what's coming. So as I mentioned to you guys earlier, we don't have any formal assessment just yet before reading week, but immediately after the reading week, right? Let's put us in perspective very quickly before we get to the lecture. You can see that assignment number 1 is going to be the main focus for the coming 2 weeks over here. And then the week right before the reading week, we will already touch upon maybe about linked list. In that case, I'll give you assignment number 2, right? So after I'll also maybe I can even release the solution a little bit earlier to you about assignment number 2. We'll see. I can also give you some review session as well. We'll see. I'll definitely keep you posted. But please notice that your programming test 1, which is going to be based on assignment number 1 recursion and also assignment number 2 linked list, will be right after the reading week. So you definitely want to make sure you practice enough. And practicing the lecture examples and also assignments, and I will also give you some practice test questions as well. Having those are a very good step, first step, but you definitely need to do more. That's something you will have to do by yourself, all right? So just want to clarify and make sure you don't really misunderstand any of the milestone for the course, all right? Any questions, please, before we do some recap? All good? Okay. So I just want to go very quickly to several slides that we kind of cover virtually, of course, last Thursday, right? So basically that's, okay, so this part here is just about, you gotta make sure you're familiar with Java and also debugger, right? When you actually program for the linked list and also recursion, you definitely will need debugger, okay? And then learning outcome, that's okay, right? And if you look at the notes from last time, right? I'll show you this page here over here. So this page here is actually very, very important. It kind of clarifies about the different terms that you will hear a lot, right? So things about computational problem And then we got algorithm. Of course, that will be the more focus in 3101. Maybe you'll take that in the summer or maybe in the fall, right? It's a follow-up course to this. And also you got data structures, right? So that will be the focus for this course. And then you got input and output. And then also we talk about correctness, no compromise. Your algorithm or your method has to be implemented correctly. And then you talk about efficiency, okay? Correctness, no compromise. And for efficiency, we're gonna focus more on the time efficiency, right? And then especially, we'll get to it today about big O. So I believe in your math prerequisite, maybe 1019, you maybe touch upon big O, right? I'm pretty sure, right? So, but this course is gonna have some very exciting application about the big O to Java code. So that's why it might be something new to you, maybe some initial struggle, but I'll get you through, at least through the example that we're gonna cover in the lecture, all right? So please make sure you review this one here. And then, so that's about the slide as well. You can read it. All right. We focus on correctness and then time efficiency. All right. And then we basically over here, it's just about before you do things mathematically, so you can actually try to measure the absolute time for how much time it will take for your algorithm to run. Right. So that's one way. It's totally okay and valid. And many people actually do that when they actually want to do some scientific experiment. That's no problem. But for our purpose, we want to do something more formal and more reliable than that. All right. So you guys can go over the example experiment, which I cover on Thursday. And then, so that's simply showing one algorithm is simply faster than the other, right? And then, so you will actually see this plot again. So when you want to maybe get very used to this kind of a plot, for example, you can see the horizontal x-axis is about n. So n here in this course and also in 3101, n denotes the size of your input. For example, if your input is an array, n will be the length of the array. And if we talk about a tree, maybe later in the course, that will be just about how many objects do you store in the tree, about input size. And the vertical y-axis is about running time. Given a particular input, what will be the corresponding time it will take for the algorithm or data structure to execute? Right? So that will be something you will see. And this is just two examples. What we're going to see today is to give you the common classes of running time functions that you will see a lot, right? So that's something I'll go as well. All right, so these are the two challenges, right? In short words, number one, if you just want to do experiments, the algorithm has to be implemented completely. It doesn't really have to, as we'll see later. We're going to talk about many ways about operating data structure, but many times, even before I talk about Java code, I'll just describe in a conceptual way about the critical steps. Even based on that information, you will be able to figure out the running time quite precisely, quite accurately, right? So that's something you want to also get used to as an engineer. You don't really need something 100% precise, executable. Not really. Okay? That might be a little bit counterintuitive, given you only came from 2030. And then we want to make sure it's actually kind of meaningful. So here, a platform is actually kind of like a factor, right? So for example, if you're really running, let's say you got two algorithms, you want to see which one is more efficient. If you simply say, I run one algorithm, it's on this desktop over here. I run another one on my Mac right here. So they are different execution platforms. So the running time you got is not really comparable, right? So you want to make sure everything should remain constant except for the algorithm themselves, right? That's something I also go into, okay? And then you want to make sure you always consider the worst case scenario, not the best case, okay? Always plan for the worst and hope for the best, right? So that's similar to the life principle, right? Always plan for the worst case, right? So we'll definitely see more about what worst case really means when we talk about different examples. All right, so we want to go beyond experimental analysis. And you will see that I will emphasize again, just make it more concrete about relative efficiency, okay? Which means you don't really have to say the absolute running time on a particular platform. Relative will be enough. All right, and then, okay, so here comes the approach we're going to learn for this course. So number one, I would say this is the most important one from last Thursday, right? Technically, it's about how you can count the number of so-called primitive operations, right? You want to count that, and this one example I did also on Thursday's lecture. Make sure you go over that, and this one example I want to leave as exercise. I'll give you the solution later, okay? Counting primitive operations, and then Today, we're going to talk about, given the number of primitive operation, can you somehow approximate it somehow, right? You don't need to be precise all the time, okay? But for this course, you got to make sure you can do both. If the question asks you to count the precise number of primitive operations, you got to make sure it's precise. But if the question only asks you to approximate the running time, you approximate, right? You got to make sure you read the question carefully, okay? We'll see. Okay, worst case. All right, so this slide number 13, very important. All right, it's more like a checklist about primitive operations. So you got variable assignments, okay, and then also you got indexing into an array. And for those of you, maybe you're taking 2031 or 2032, the C course, you will see that actually about array indexing is really about going to some memory address directly, right? So calculating the corresponding address to go into is not expensive. Okay, so that's why array indexing or even assigning something to the array, some element is very constant, very cheap. So all the arithmetic, relational, logical operators, you will see they're also constant. Okay, and also if you want to access the attributes in an object, that's also also like an address lookup. So that one is also constant. Now, also return statement is also constant. Method call, right? So you will see that there was some discussion there on the notes right here. Okay. All right, just talk about if you actually want to do some method call in general, there could be two different cases, right? Depends on the method itself. For example, if the method you're calling is only doing hello world, cheap. On the other hand, if the method you're calling is doing some sorting, of course, it will be more expensive, right? So it really depends on the method call. So that means whenever you're seeing as part of your algorithm, making a helper method call, you don't really know the exact running time until you also analyze precisely that method itself, right? Like a step into, all right? That's also good. And then this, it will be another important example you want to make sure you really understand. So this one here is really calculating the precise number of primitive operations, right? So for example, you can see that the answer at the end over here would be 7n minus 2. So that means if you somehow calculate 7n minus 1, 7n minus 3, they are considered wrong. So here, got to be exactly 7n minus 2. Right? So please be careful. If you are asked to calculate the precise number of primitive operation, it has to be exactly this precise. So that's a very good way to really train yourself to really analyze each line one by one and be very careful about which primitive operations are involved. Right? So study this example very carefully and then redo it if you want to. All right? Okay, that's pretty much from last time. Any questions? A quick recap. But of course, don't take my recap as the replacement for the actual lecture. You have to study that, right? There are many things I didn't quite mention in the recap. You have to fill the gap. Okay? So we're going to start from today's, we're going to continue, build on that. Okay, so let me just go for, so you will see that slide number 15. Okay, so this is just another example for counting the primitive operation number, right? I will leave this as exercise for you. All right, you have the iPad notes. But I'll just put it here, exercise. Okay, you can try to calculate it. I do have some guidance question over here. That's something, of course, in the test, I wouldn't give you these questions anymore. That's something you have to ask yourself. But, you know, for this one, it's okay. That's only your second example. Do it, and then I'll give you a solution a little bit later. Okay, or you can just drop by. If you want to go over your answer with me, that's fine too. Okay, good. So today, we're going to start from here, okay? Let's start from here right away, okay? So this slide here is really making a transition. Now, we are going to move from absolute running time to relative running time. Once we get there, we'll talk about mathematical property for big O, right? So this page will be more like an important transition, okay? I should go for some bullet point, and then I will start with something to build up from scratch, okay? So here is something we assume, which is also sensible. Each primitive operation, variable assignments, array indexing, they takes approximately the same time, but depends on the platform. Maybe this desktop over here is very old machine. It maybe take 10 milliseconds, for example, for variable assignments. And for maybe my Mac is a little bit newer, back in 2015, this might be 5 milliseconds. But for your maybe a Mac M2 or M3, it might be even faster, right? I'm just saying the absolute running time for each primitive operation, similar but not exactly the same, right? Depending on the model and also the operating system. So we just simply say a little t over here. Okay, I'll talk about the t in just one moment. So here is a critical question. So let's understand what this question is really saying, and then we'll go into building up something for our understanding. Okay, so we'll read this question together. So we're asking, if I know about the number of primitive operation, let's say 7n minus 2 in that find max example. 7n minus 2, given this, how do we know its absolute running time on a particular platform? And the follow-up question is it really necessary to know the absolute running time? Right? So that's something we want to think about, right? So you can read the rest, but I'm just going to build it up to make it more precise for you. Okay, let's take a look. Okay. So let's now make that critical question very, very explicit. We're basically asking, so the big question is, when we are given the number of primitive operations, and from that find max example, right? So when we have, let's say, 7n minus 2. Let's try to interpret this 7n minus 2 a little bit more. The n here is about how many elements are there in the array, right? So now we have different choices. For example, this one is telling us when the array has only one element, that means we got 1 times 7 minus 2, which will be 5 primitive operations involved, right? You just plug in the number. And if the array is a little bit bigger, n is equal to 10, it's going to be 10 times 7 minus 2, which will be 68 primitive operations, and etc. Of course, the bigger the array size, the bigger the corresponding number of primitive operation that will be involved, right? That's exactly what 7n minus 2 really means, right? You want to make sure that one is understandable, okay? Given this, how do we go from number of primitive operations to two possible, we can do two possible route to do analysis, okay? Okay, so we can either go to absolute running time. For example, we may measure that, let's say milliseconds, right? Or maybe something even smaller. Okay, milliseconds should be good enough, you get the idea. Or we can simply do relative running time, okay? In this case, without considering t. Okay, I'll explain what t is. So we got these two possible routes. So I want to show you intuitively why choosing the second route without considering t will be good enough for our analysis, right? Let's make it more explicit, right? It's more about conceptual clarification, right? So let's now start with the little t I have over here, the t. So we have a t here. Let's understand exactly what t really means. So t represents the exact or absolute the time that will be taken to execute a primitive operation. So whenever you see me writing PO, that means primitive operation, right, for this course, okay? In some execution environments, which means the value of t might be very similar between platforms, but they're not exactly the same. Okay, let's make one example. So let's say, for example, if I have some Mac, let's say M1, okay, the t might be, let's say, 2 milliseconds, just some value to compare. On the other hand, let's say I use my Mac over here, it's pretty old. So for example, if I got some Mac from year maybe 2014 or 2015, right? That was slower. That one could be maybe 6 milliseconds. Okay, so here you can see the value here, 2 versus 6. they're kind of similar value, right? But they're just different because different platform. All right. So now to really see why t is not so important for our formal analysis for the rest of the course, let's draw a table to consider like a different possibility. All right. Let's draw a table here. I'm going to draw a table over here, and then I'll go over with you about different dimensions for the table. Okay. So here, and also here. Okay, we're going to talk about two things. For over here, the first dimension, we're going to talk about relative running time. Relative running time. And for this second dimension here, we're going to talk about absolute running time. All right? And we'll see. And let's talk about two different algorithms, hypothetically. All right? So I'm just going to divide into two algorithms. So let's say I got 7n minus 2, right? That's the phi max. I got another one. Let's say it's 10n plus 3, all right? So these two over here, okay, are simply the running time. These are the relative running time of two alternative algorithms solving the same problem. That's why we're comparing them. We somehow want to find out which one is more efficient, right? Solving the same problem. Okay, of course, the critical word you want to pick up is two alternative algorithms. And then they are solving the same problem. Okay? And we're considering the running time also absolute by considering two platforms. Platform number 1, platform number 2. All right. So I'm just going to put it here. Okay. Either we have our Mac M1 or we have our Mac maybe from the year 2014. All right. Okay. Let's fill out the matrix over here, right? It's hypothetical, but it's very informative to really convince ourselves why t here is not so important. Okay. Let's first talk about these two, right? If you talk about these two, what does that really mean? That means for the same algorithm, we try to compare what would be its execution time in this platform versus this platform. Right? That's what we're doing. Okay, let's do that first. Okay, the same algorithm. We're not even considering the second one just yet. Okay, so that one there. Oh, one more thing I got to say. If you also look at the n here, of course, the n here as well. And as I said earlier, it's about input size. Why don't we assume for now the input size n is equal to 100? Let's say we got an array of 100 elements. You can make it 1,000, 1 million, doesn't really matter. Okay, 100. Okay, we got all the necessary information to calculate. For this one here, how do we calculate the absolute running time for this algorithm here? Basically, we have to replace n here by 100 and then multiply by the absolute execution time for this, which will be 2. Right? I'll write it down, right? So this will be basically 100 times 7 minus 2, and then times 2. You just be reminded, this is t, and this one here is n, right? It's a very simple math, right? But conceptually, you got to know that we're considering both the input size and also the execution time for each primitive operation. Okay. Similarly, we can do the same algorithm, but now you can see this part here, 100 times 7 minus 2. This part here is the same. But now, since we are executing it in different platform, so it's going to be times 6. Okay, so this is just another t. You can think about this is t1, and it's like a t2. But input size is the same, right? So now we want to look at these two numbers, right? You can see that what really matters is really this part over here, the relative right here. Multiplying it by either 2 or 6 or another similar number, it's not going to impact our conclusion anyway. You're still talking about the fundamental idea about 7n minus 2. Multiply it by 2, multiply it by 6, it's not going to give you any extra information. So that's why in this case, we can drop t. Okay? We just don't need to consider it. Okay? So let's now say this. Okay? Conclusion number 1 here. So we got T1 here and this one here. Okay, I'm going to say when considering the same algorithm in can, it's not necessary to consider the value of t in different platform. It's simply not necessary. All we need to worry is about this part over here and this part over here, and they're really the same. You don't need to bother, right? We can be platform independent. That's point number 1. All right. Point number 2, which is more important. What about we consider these two like a 7n minus 2 and 10n plus 3, right? And we got to make sure we do the fair comparison. You shouldn't really compare, let's say, this one here, M1 for algorithm number 1, and also M year 14 for this algorithm. It's not fair. It's got to be the same platform, right? So let's say this one here, if I want to compare which one is more efficient, I should really fill out this cell over here in the same platform, right? Let's write it down. That one there is going to be, again, 100 times 10 plus 3 multiplied by the same t, right? 2. Okay, you can see that it's the same t, the value. Okay, let me highlight it. You can see this part here is really the same, whereas this part over here is different. So now the question is, in order for us to really know about whether this or this is more efficient, they're multiplying themselves by the same factor 2. So our decision shouldn't be impacted by this. We can simply ignore them, drop them. All right. Okay, that's the second point I want to make. Okay, so that one there. So also this one here, and also this one here. Okay, I'm running almost out of space, but I'll put it here. Okay, so this will be the second point I'm going to make. Okay, the second point is when considering different algorithm, it's not necessary to consider t in the same execution environments. All right, because over here we can just focus on just the relative running time. Okay, let me recap very quickly. Maybe you're still taking notes. So what we're really trying to say here is, once you calculate a primitive operation, let's say either 7n minus 2, 10n plus 3, maybe 7n squared minus 4, something like that, right? Doesn't matter. So that relative running time should be sufficient for us to do any further analysis with much precision. You don't really have to consider the platform factor about what's really the absolute running time for each algorithm to really execute, right? Just not necessary. It's a very important transition, because from now on, I'm not going to talk about either of the platform anymore. I'm also not going to talk about T. It's just not important. Right? It's an important concept for you to grasp. Okay, question, please, Daniel.
Because right now, the input size is 100.
Right?
If it was 500,000, for example.
Yeah.
Multiplying it by 2 make it 1,000,000.
That's good. Good question. So let's say you're basically talking about, okay, let's say this. So let's say n is now 100. If n becomes, let's say, 5 million, what we're going to do is 5 million is going to be applied to here. So this will be 5 million. And this one here will be 5 million. So 5 million for both, it will be enough. Further applying 2 here, it's not going to impact the result anyway. So we can simply safely to say, without even this factor 2, we just based on these 2 numbers, we can already say something meaningful, which we'll see. All right? Okay. So this little small factor over here that's going to be applied to both of them is simply not necessary. Right? You can just drop it without impacting your analysis result. All right, good. Okay. Alrighty. Okay, let's do a little bit more. We can go for another 10 minutes and then we'll take a break. Okay. So let's now move on to relative running time. And the next slides I'm going to go over. So this part here is done. Oh, actually, I think the one I just did was slide number 16. Okay. And we're going to do slide number 17. So 17 here is just going to give you some relative time example. And then there will be certain terminology I want to clarify, things like a multiplicative constant, highest power, and also lower terms. So things like that. Right? Let's use one example and then talk about it. Because identifying these terms will help you approximate the running time. Once you approximate the running time, it will be the best guess. Based on the best guess, you also had to prove it. In order to prove it, we're going to learn about definition for big O. Right? That's kind of the flow. Okay, let's now take a look at this one example, right? It's actually quite nice because you can see we got, reasonably complicated. We got n squared, we got n, also we got log n. Oh, actually, so to be more precise, we got n squared, we got n, also we got n log n, right? So that's something you will see quite often. And for this course, whenever you see any log without the base, you can assume that the base is 2. Okay, like a computer is binary. Okay, I'll write it down first. So whenever you see like a log n over here without any base, it will be as if I said log 2 n. Do you guys remember what log n really means? Right? If I say x equals log 2n, what does that mean? That means, go ahead, Daniel, n equals 2 to the x, right? Okay, I'm pretty sure you guys know, right? Be sure you recall that, right? This will be important. Later on, after the reading week, once we start talking about binary trees, etc., you will need the log because naturally, binary tree will be base 2. So you have to deal with log and also exponent. Okay, so it wouldn't hurt if you just go back to your maybe calculus class and then review some notes about log. I think that'll be sufficient for this course. All right, so let's now think about this term. I'm going to rewrite it here. I got 7n plus 2n log n. And then plus 3n squared. All right, just to begin with, you can think about this term over here, n here, it would be as if you wrote n to the power of 1, of course, right? And by the way, if I have another one, let's say if I simply got 7, 7 would be as if you wrote 7 times n to the power of 0. Sometimes writing these explicitly will also help on identifying the pattern. Okay, I'll just write it down here. You might see that, we'll see that a little bit later. Okay, I'll just put it here as a side notes right here. Okay, let's now consider this one here. Okay, typically, if you're given a running time function, relative running time function like this, the first thing to do, identify the highest power. All right, highest power. For example, you can see that the highest power cannot be this one here because 1 here is strictly less than 2 over here. So cannot be this one. It's got to be something that's lower. So now we got to determine between n log n. So here you cannot just look at n and also log n in isolation. You have to look at n log n altogether. Right? So n log n versus n squared. We want to see which one is higher power. Right? See my point here? All right. So now which one is higher power? N squared? Yes, that's right. Yeah, definitely. So without really going to prove it, I want to show you some intuition. Whenever you have any doubts, you can try to maybe somehow plot out the function to see which one is going to, okay, I'll write it down. Right? some visual intuition. Okay, so you can think about visual plot. A function with higher power grows faster. Okay, that's the most intuitive way you can think about function, right? So now let's talk about just log n over here, because you can think about this one here is like n times n. So n here is really the same. So we only need to compare log n versus n to see which one's higher power. That'll be enough, right? Just intuitively. So we can just plot it out, okay? Approximate. So let's do that plot over here. Okay, so here, remember we got horizontal and vertical axis, right? Horizontal will be just the size of the input, n, and vertical will be f of n, the relative running time, rt. Okay, so now we're going to compare n versus log n. Okay, it's definitely not difficult. Maybe you already know log n is going to grow much slower than n, but let's just plug it out. Okay, so you're going to see something like this. So this will be n. All right. So for example, you can see that. So this part over here, also this part over here, and also this part over here. Okay, I just want to be a little bit more precise. Okay, so you got 1 and 1, 2 and 2, and 4 and 4. Right. Also, you can think about n will be n to the power of 1. Right. Okay, that's linear function, which is, for example, if you do a find max, or if you want to search an array from left to right, that'll be linear. Right. That's a very typical function. Right. That's linear. That's good. And I want to point out another one that's also very important. It's so-called a constant function. Okay, so constant function will be something just like this, for example, which means the function is a flat line. It never grows. It's basically flat, right? If you take the derivative, it's going to be 0, basically, right? So here, this will be, you can think about it's simply just 1. On the other hand, you can think about it will be n to the power of 0. Again, it might seem a little bit silly to actually say n to the power of 0, but believe me, later on we're going to see. In other contexts, explicitly identifying something to the power of 0 can actually help you see the pattern precisely. Okay, well, I'll save that for later. So now, where should we do log n, right? So we know that, for example, log 2 will be 1. Log 2 will be 1. And also, log 4 will be 2. Log 4 will be 2, right? So roughly speaking, and also log 1 will be 0. Convinced? All right? If you do that, roughly speaking, it's going to be something like that. All right? So this tells us that log n has lower power. Oh, let me put it the other way. You can think about n has higher power than log n. Okay, we'll see another more complete plot, but I think that this one might be just worth doing from scratch. All right, so now let's analyze just a little bit more. Okay, so now if you look at this one here, okay, you can think about this one here. This is more like a power 1. And this one here is actually growing slower than n. You can think about it's point something. Okay, it's a 0 point something. So overall, it's a power of 1 point something, which is strictly less than 2. Right? So that's how I figure out. We don't need to go for very deep mathematical proof. We don't need to, okay, for this course. All right, so now we have decided n squared is the highest term. Okay, let's now identify that quickly. N squared over here is the highest power. What does that really mean? Highest power. Okay, that means asymptotically. Asymptotic is something you will see for sure. You know, if you look at the lecture itself, it's called asymptotic analysis. That means towards infinity. All right. So asymptotically, this highest term, n to the power of 2, dominates over other terms. Okay, that's something we'll elaborate a little bit later. Okay, asymptotically, highest term dominates. All right, as soon as we see that this is the highest term, later on we can just, let me go a little bit ahead. I can already say approximation, it is big O of n squared. Okay, I'll talk about big O maybe after we take a break. Okay, a little bit later. Okay, big O of n squared, which correspond to the highest term. Okay, keep that in mind. Okay, let me see. Let me say two more things. A few more. And then if you look at all the constant factor to every term, it's called multiplicative constant. Let's also make it explicit. You can, let me just highlight it. You can see the 7 here. You can see the 2 over here. And also the 3 over here, right? It's called multiplicative constant. This one here, and this one here, okay? It's called multiplicative constant. Right? Every term. Even if you have, let's say, even if you have just n over here, they still have a multiplicative constant, which is just 1, right? Finally, this is the highest term, meaning that every other term is considered lower terms, right? It's more like a collective saying. Okay, so finally, we're going to say everything other than the highest term will be the lower terms. Of course, it may refer to this one here is one lower term, that's another lower term, but you should use the lower terms for all of them, everything else, okay, other than the highest term. Guys, any questions so far? Okay, good. Why don't we take a short break, take attendance, and then we'll continue. Okay. Yeah, you can just get your iClicker ready, please. Right, before the break, we clarify about highest term, lower term, multiplicative constant. We'll still need them very soon. Okay, so let's move on. So let's now just go over very quickly about the very common classes of functions that you will see very often, right? So let's see here. Okay, so this plot here is also on the slide, very important. Keep them handy. You know, something it might be useful for you to just remember what's really there available that you will see very common. Okay, so we got constant, logarithmic, linear, and log n, quadratic, which be n squared, cubic, and third, n to the power 3, exponential, like a 2 to the n. All right, so these are the common ones. You might see something maybe a little bit different from these, but that's more or less similar. For example, in 3101, you might see something different too. All right. And let's see how you're supposed to interpret this plot here. Let's read it together a little bit. So constant here, right here, the one in green. Let me highlight it first. It's right here, right? Which means it stays completely flat right here. Doesn't matter how large the input is, right? So let's just choose that in isolation. That could be sometimes could be confusing. To start with, that one would be the slowest growing. So this function here grows the slowest, which means it will be the dream running time for your algorithm. Of course, if you're only doing hello world, it's constant, right? But if you're doing, let's say, something that's even, let's say if you're doing searching, if you're able to make a constant, which is not very likely, right? That'll be great. Okay, let's see running time very quickly, just for this one here. So if I say my f of n is, let's say, 1000. So this is considered as constant because you can rewrite it as 1000 multiply n to the power of 0. Remember before the break, we said that you just need to choose the highest term, which will be n0 alone. And then you can even disregard multiplicative constant. So this one here, you can just guess right away, it's big O of n to the power of 0. Or you can say big O of 1. Right? That's something you want to get used to. So what's really amazing about this is, if I try f of input size 1, it is going to give you 1000. If I try input of 10,000, it is still going to give me 10,000. If I try input of 1 million, it will still give me 1,000 and etc. Right? The running time remains the same. In some way, the running time doesn't depend on the input size. You can put it that way, right? But I would say realistically, you wouldn't have so many constant functions that would be so important for you to design. Normally just a routine task. Okay? Let's see some more functions, okay? And you will see that the other extreme will be exponential, right? So this one will grow the fastest. Okay, so you can see right here, basically they grow exponentially like that. Even for relatively small input, you can see only up to maybe 10 to the power of 2, you can see the running time is already exponential right here, right? Exponential. That's something you want to avoid getting to. But I would say sometimes having some exponential algorithm, I know, is really bad. However, let's say sometimes when you do recursion, if you simply just try to exhaustively figure out all the paths in some way, it's 2 to the power n exponential. But for smaller input, it might be acceptable. It's all about what's really acceptable within your application, right? If you don't really have like that large input, I think having exponential could be acceptable, could be. Right? But of course, you want to try your best to make it as efficient as possible, theoretically. Let's see a few more. So you can see the linear right here. So we have linear right here. So you can see linear is right here. Okay, so that's the orange one. Okay, and also the logarithmic right here, right? That one there is just about here, which is consistent with the diagram that we draw before the break, right? You can actually look at different functions right here. Just remember the order, right? Not necessarily gonna memorize it, but I would say, these are just what you learned from the earlier math classes. You might know them anyway, right? Just make sure you know them. Okay. All right, let's now talk about one more example, okay? So this one here is really about slide number 21. Okay, but let's see. All right. Yeah, so this one here is just saying, in this course, we're gonna really just consider worst case scenario, right? If you want to search for an array, you don't really say, oh, array, the best case, maybe the element is right there in the first element, so it's constant. Not really. We think about, in the worst case, if you want to search through an array, the element might be very close to the end, which will take you linear time, right? So here, I also mentioned about average case analysis. This is not something that we're going to cover in this course, but in 3101, you will run into something called amortized analysis or average case analysis. That's something that's going to involve more math to really figure out exactly the time. Right? That's something we'll cover in 3101. Okay, not this course. Just remember, for this course, always think about what's the worst. And then asymptotic analysis is really towards the limits. We'll get there once we get to the definition. All right, so let's talk about two examples very quickly, okay? All right, so now let's say we got two examples, right? So for each example, we got two possible, let's say two alternative algorithms for the same problem, right? Let's talk about these two. For solving the same problem, algorithm number one, algorithm number two, right? We got these two. Now we're asking asymptotically, meaning that assuming that input goes towards infinity, which algorithm has a better running time? If I didn't say asymptotically, in that way, you may have to plug in some number to figure out, which one maybe up to 100 is doing better. But now since we say asymptotically, things get a little bit simpler. What you're gonna do is you simply approximate using the principle we set before the break. Identify the highest term, drop everything else. All right, let's try. What we're doing here, okay, let me just emphasize, we're talking about asymptotic running time. And also here, we are trying to approximate. Let's say R1, RT1, RT2, right? RT1, highest term, n squared, okay, over here. RT2, also n squared. Good. Once we have identified them right here, n squared right here, also n squared right here, everything else can just be disregarded. This one here, all the lower term gone, all the lower term gone. So this one here is really just about n squared. This is also n squared. Conclusion you can make would be they are equally efficient asymptotically. Okay? So they are equally efficient. However, it is very important for you to add asymptotically. Asymptotically. Right? That's a very important context. Okay, since we are approximating. Okay, one more example here. This one here, highest term, cubic. Here, highest term, n squared. Right? Straightforward. So for that one there, we're going to say this will be the highest term, and this will be the highest term. Apart from that, drop everything else. You can drop all the lower term, drop this multiplicative constant, and drop all the lower term. So this will be n to the power 3, and this will be n to the power 2. So now, in order to see which one is more efficient, we want to see which running time function is going to grow more slowly towards limit, towards the infinity. Okay. So now, which one is more efficient? This one here, right? Okay, awesome. Okay, okay, let's write it down. So here you can say this one here, RT2, is more efficient, which means taking less time. When the input size n goes towards infinity, right? I'm just writing a little bit more informally, right? So we are really trying to approximate when the input size goes towards infinity. And it's more efficient asymptotically. Again, it's important to say asymptotically. Okay, asymptotically. Questions, please, so far? Okay, okay. Okay, I want to do one more, like a summary before we see. Now we should be ready to see the formal definition for big O. Okay, but before that, I want to just a little bit more, just to give you more notes so you can just get prepared. All right, so now we're done with this one here. In theory, so there are other asymptotic bounds that we can actually do. It can be, so there are big O, there are omega, and also theta. But for this course, we only do big O. There's even something called little o, but we don't need to worry. We only focus on big O. I think even for 3101, I think at least if you might take it with me, maybe later, I'm also going to focus on mainly just big O. That's something we're already familiar. But once you see the formal definition for big O, for the other formal notation for the other asymptotic bounds, they are defined in a very similar way. Okay, so, but anyway, for this course, big O. And then slide number 23 would be something I want to go for the next maybe 15 minutes or so. Right? We'll see how much it will take, but definitely it will be the main thing for today. Okay, so this is the formal definition. You will take a look later, but let me just get you started. Let's build it up. Okay, we start with this. So there are basically three things you want to keep in mind whenever you talk about the definition for big O. Three things. Okay, number one. So we got something called f of n. So this represents the relative. Again, you can think about it's a relative, right? Of course, we're not going to emphasize the relative anymore because we already assume after that transition. Running time function. Meaning that if you give me your input size, what n is, using that function, I can tell you what would be the relative running time. Or you can think about it's about roughly the number of primitive operations involved, right? Either way, number of primitive operations involved. right? The famous example we have been seeing is 7n minus 2, right? So that one we know pretty well. So start with this, right? So whenever you want to talk about big O, this is the main character, right? So we want to say, given the running time for some algorithm I have designed, now I want to see which asymptotic upper bound family it belongs to, all right? So now, how do we define a family, okay? And family is more like a set idea, which you maybe also learned in the previous discrete math course. I'll also review the necessary bit later, okay? Let's now start with, okay, let's see some diagram, first of all. Okay. The purple here is what we said, the big O family of some function called g of n. So this is the second component you want to keep in mind, g of n, all right? And the way I think about the g of n over here is a reference function. Something for us to really take as a reference to decide whether f of n should be a member in the family, right? So now in this case, if we say f of n is a member there, right? We can use a set notation. You can say f of n versus the big O of g of n, right here. And we can use that set membership, right? That set membership you saw earlier in the course, in the math course. Okay. Okay, I'll get there in just one moment. So let's talk about g of n. I'll write it down. So the g of n is simply a reference function. When you actually state the final facts about f of n should be a member of big O of g of n, here the g of n is just by itself. However, when you are working out the proving process of big O, g of n typically doesn't really stand by itself. You have to further manipulate it by some constant. Okay, I'll write it down. Okay. Further manipulation on g of n expected. Okay, more precisely, when I say manipulation, I really meant given the g of n, somehow for you as a prover, to actually prove something about big O, you have to choose that constant called c. Okay, that's something you will see in the formal definition. I'll write it down for now. Okay, so it's going to be c. All right, and I'm pretty sure you know that maybe from your linear algebra course, if you maybe either linear algebra or maybe calculus course, if you consider g of n versus c times g of n, what's the difference? I'm looking for some term. Let's say this. If I got g of n is simply n, I choose c to be 9, for example. 9 times n. How do you see the difference between them visually? I'm looking for one word starting with S. Oh, slope. Brilliant. Exactly. That's what I'm looking for. Okay. So here, that's exactly, right? Now I'm going to visualize to you, okay? That's very important, okay? Think about this one here. Basically, multiply g of n by c. We effectively modify the slope of g of n, okay? You can think about this is more like a steeper version of g of n with larger slope, right? And typically c cannot be negative, by the way. You just choose a positive, right? All right, so now we got g of n, and also we got c times g of n. So these are, again, so these are the three things. Running time function here. Also the reference function, and also the modified version of g of n. So these are the three important components when you talk about definition for big O. And usually, the goal you will be facing, okay, will be you want to prove. Usually you will take a guess first and then you prove, right? You want to prove that the f of n. So there are different ways to say this. I'll show you. It's on the slides. F of n is the big O of G of n. All right. So on the slides over here, I'll show you quickly. So there are different ways to say that, right? Either you can say f of n is a member of the family of big O of G of n. That's what I said on the notes. Or you can say f of n is big O of G of n. So people usually say these two. You can choose either one, right? Doesn't matter. Okay. There's one more thing I want to, I think that's okay. I think that's good enough for now, right? So now the only thing I didn't really quite define is about how do we determine right here this membership? Under what circumstances? Under what circumstances can we actually say f of n is a member of this big O family based on G of n? I haven't said that just yet, but that'll be up to the formal definition. All right. Any questions so far about this kind of conceptual sketch over here? All good? All right, let's now get formal. Okay. So the formal definition is actually right here. Okay, but I'm gonna go over that and also visualize it. Okay. That's a formal definition. Well, actually not very long, right here. So just keep ourselves reminded. What we are really doing here is think about this is the family of the big O of G of n, and then we want to show that the runtime function f of n is actually a member of it, right? So you can think about f of n is right here, and G of n is right here, right? That's what we're going to show, okay? So under what circumstance? Here's the circumstance. There are two things over here. There's some multiplicative constant C. C here is some multiplicative constant to modify the slope of G of n. All right. Modify the slope of G of n. We're going to talk about how you can choose the C. And then you have to choose another constant. And that constant there is n0. Okay? n0 here, let me put down and then I will explain to you what I really meant. n0, the 0 subscript is basically say it's a starting point because it's like an array, right? Indices start with 0. So n0, n itself is about input size. When we're saying that, there should be some starting point of input size from which some property should be satisfied. Okay? I'll write down first and then we'll go over. So n0 will be the starting input size for so-called upper bound effects. Upper bound effect to occur. Okay, I'll read it again just in case you're taking notes. Okay, so n0 here is so-called starting point size for the upper bound effects to occur. All right, now let's take a look at the equation very quickly and then we'll visualize it. So this less than or equal to over here is exactly what I meant by upper bound. Okay, so you can think about less than or equal to here is you can read it as upper bounded by. Okay, or you can say is upper bounded by, all right, I'm saying the running time function f of n starting from n0 is going to be upper bounded by the g of n multiplied with some chosen c as the multiplicative constant. Let me say that once more. Okay, we're saying that f of n, the runtime function, starting from certain input n0, is always going to be upper bounded by the reference function with some chosen multiplicative constant. All right. Okay, you want to get used to the definition, but let's now visualize it. Okay. The diagram you see over here is a very standard, like a textbook diagram. I think that's pretty good, very informative. We can really see quite many correspondence there. But somehow you can see we are only showing f of n. Okay, let me just highlight them first. Okay, you can see that we already got f of n right here, and also we got. You can see here we already got a modified version of g of n, right? But the actual g of n is not really shown. So this diagram here is not exactly complete, but don't worry, I got another one, which I drew by myself. I will show it to you a little bit later, okay? But you just got to remember the c we are choosing here is being reflected right here, right? So that's a c. And then the g of n, the reference function, is right here, okay? But it's not really showing g of n by itself. Strictly speaking, you don't really need to see that. You only need to compare these two. But I'm going to show to you a little bit later. So think about this function here is right here. So now these are the two functions, running time function and the modified reference function. Now we want to consider the upper bound effects. As you can see, right? These two functions are kind of funny. They're kind of twisted somehow, right? So you can see there is a middle point right here. Before this point, you can see this equation here is not the case. That equation is saying f of n right here should be less than or equal to c times g of n. This. Is this less than or equal to that? No, it's not. On the other hand, if you look at to the right of this point over here, f of n right here, always less than or equal to c times g of n, which is right here. You can see less than or equal to is actually right. So this one tells you when you look at these two functions over here, the so-called upper bound effect does not need to be true all the time. As long as you can find some starting point n0 from where the upper bound effect will be true, then that'll be okay. Okay, let's now write it down. So what I will do is, let's do this. Okay, first of all, let's see when the upper bound effect is not the case. So you can think about right here. Okay, so this part here, I'm really talking about when the input size n is strictly less than n0. Okay, so n0 is right here. Right, so that as an n0, we're talking about in the formal definition, right? And in that case, you can see that f of n less than or equal to c times g of n is simply not the case, right? Because this is not really less than or equal to that. It's not, right? It's false. All right, number one. So that means you cannot choose the n0 to be any value less than that. Right? On the other hand, if you see that starting from n0 itself, which I'm going to use a different color, think about starting from here. This one here, this part here, right? This part. Okay, this part is where the upper bound effect holds towards infinity. So this one here, basically we're saying, starting from n equals n0 and onwards, f of n, the running time function indeed less than or equal to the multiplicative constant we choose times the g of n is true. Right? You're going to say when it's false versus when it is true. Right? You'll see the green one always strictly upper bounded by the blue one. Right? Are we okay with this? Okay, that's formal definition. Okay, so I think we have a little bit of time just to do a quick example, very quick. Okay, so let's see one example here. Let's say we got example function, f of n and g of n, right? That g of n is simply n. We might expect to multiply some c to it just yet, a little bit later. Let's say f of n is an plus 5, right? So now let's say rather than proving, okay, let's see this. If I have c being chosen to be 9, what should be the value for n0 in order for the upper bound effects to occur? Before that, I don't know, maybe you have some answer. Okay, maybe you already calculated. Right? It's very easy. You just got to equate two functions, right? But before that, can n0, let me just ask you this question to help you a little bit, okay? So just remember, we already have chosen the c to be 9. Okay, just keep that in mind. And now we're basically asking what n0 should be. Let's say I give you one value for n0. You want to validate if n0 is valid. How about that? Okay. Now I'm going to put here. Can n0 be just 1? It's a valid question for the test to test your understanding. Now I'm asking, given the f of n and also given the g of n, also I fixed the 9 being the c. Now can n0 be 1? Let's say true or false. Can it be yes or no? Can it be? False, okay. For those of you who might be thinking false, okay, let's see exactly, right? It's a little bit tricky, could be, okay. Let's be very logical here. If it has to be n0, it need to be 1. That means starting from 1, this upper bound effect should be the case, right? So let's try to verify that. So what we are really trying to say is f of n0 should be upper bounded by whatever c we have chosen multiplied by the g of n0, right? So this is the universal. This is always the case. You can always make sure you understand this one first. And now we can plug in different value, right? The n0 we are assuming is 1. And also the f of n is here. The g of n is here. And also the c is right here. We got everything. Let's plug it in, okay? So what we have is f of 1, which will be, let me just write a little bit more. F of 1 less than or equal to, c will be 9. 9 times the g of 1, right? And then f of 1 over here, you plug it in, that'll be a plus 5 less than or equal to 9 times g of 1 should be, right, what's g of n? And here, just 9 times 1. Okay, we are asking 13 less than or equal to 9. Is it the case? No. So the answer should be no, but you got to justify it, right? No. No. Right, so it's a very small test just to make sure you understand what upper bound effect really means. Another question is, what should n0 be? I heard 5, okay, good. How did you figure? You're going to try values, right? I'm guessing, okay? That's good. That'd be a little bit more systematic. I like it, okay? So here, you can think about, we just want the equal sign here to be true, right? So I'll put it here, aside. So what we really want to do over here, we want to say f of n0 exactly equal to c times g of n0, right? F of n0 is going to be 8n0 plus 5 equals, and c here, we have chosen that to be 9. 9 times, and then it will be just n0. Agree? Okay, move the turn. You get n0 should be exactly 5. But it is more important for you to see that the way I figure out is by simply referring to the equal case right here. All right? All right? Guys, any question? I got about 1 minute or so. How about we do one quick example, right? Quick one. I think, let me see. You know what? I changed my mind. How about you guys can go a little bit earlier? I think that's good for now. Review the big O definition before Thursday, and then we're going to continue from there with lots of examples. Thank you. I'll see you later.